This is Bob Capetta from the University of Illinois at Chicago, and this lesson is an introduction to differential equations. So this is an example of a type of differential equation. We're saying dy dx equals 2x and y of 0 equals 5. This means when x is 0, y is 5, so we're going to keep that in mind. We want to solve this differential equation, and maybe you can think about this and sort of do it mentally. Think of a function y whose derivative is 2x. I bet you can come up with an answer, and then knowing that y of 0 is 5 enables us to find the specific one. But let's go through our process. So we're going to look at dy dx is 2x. Our goal with this strategy is to separate the variables, get all of the y's on one side, get all of the x's on the other. So we're going to, in a sense, think of multiplying both sides by dx. If I do that, the left side is dy, the right side is 2x dx. And now we have successfully separated the variables. Integrate the left side, integrate the right side. Now there is no number with the dy, so we could call it 1. Tell me a function whose derivative is 1 if we're thinking of y as the variable. Over on the right side, take the integral of 2x. Tell me a function whose derivative is 2x. You may be able to do both of those mentally. We're going to go ahead and integrate both sides. So the integral of dy is the integral of 2x dx. Again, thinking of a 1 there. Tell me a function whose derivative is 1. Well, the derivative of y with respect to y would be 1. Tell me a function whose derivative is x squared. Well, is 2x. Of course, the derivative of x squared is 2x. So we could think of this as y equals x squared plus c. If you'd like, you could also pull the 2 out in front. The integral of x is x squared over 2 using the power rule. 2 times x squared over 2 gives us our x squared for our antiderivative. So we have done the first part of the differential equation. Now we need to solve for the constant. If I give you an initial value, then you need to go ahead and plug that in and see what you get. We have y of 0 is 5, so that means when x is 0, y is 5. So if we plug a 0 in for x and a 5 in for y, we will say what? We'll say 5 is 0 squared plus c, 5 is 0 plus c, 5 is c. And then we plug that 5 into this equation, and our final equation is going to be y equals x squared plus 5. So we started with a differential equation. Our answer is an equation. If I didn't give you the initial value, if that was left off, then y equals x squared plus c is a perfectly acceptable solution. But I did. We plug in the 0 for x and solve for c. My next example is dy dx is 3x times e to the negative x squared. Again, we want to separate the variables, and I'm telling you here that y of 0 is 2. So when x is 0, y is 2. I want all the y's on one side, all the x's on the other. So we're going to actually need to multiply both sides by dx. Doing that, I get dy is 3x e to the negative x squared times dx, and then we're going to integrate both sides. Integral of dy is going to be the integral of 3x e to the negative x squared dx. We have separated the variables, all the y's on the left, all the x's on the right. Once we've done that, then we can integrate both sides. The integral of 1 with respect to y, integral of dy is just y, and this is going to take some work. That's going to require us to do a U-substitution. So let's go ahead and take that first integral. Integral of dy is y. Now we have y equals the integral of 3x e to the negative x squared dx, and y of 0 is 2. So when x is 0, y is 2. Keep that in mind. So to do this, we're going to need to do a U-substitution. U is negative x squared. Now the derivative with respect to x of u is the derivative with respect to x of negative x squared. The derivative with respect to x of u would be du dx, and the derivative with respect to x of negative x squared is negative 2x. Now in U-substitution, I like to solve for dx. That's my strategy. So in a sense, we'll multiply both sides by dx. Du is negative 2x dx. Then divide both sides by the negative 2x, and we've solved for dx. Du divided by negative 2x equals dx. So how does this work with our U-substitution? Negative x squared will be u. Dx will be du over negative 2x, and we'll see if all of the x's have canceled. That's our goal with U-substitution. You'll notice this x and this x cancel. That's 3 over 1 That's negative 2 downstairs. 3 divided by negative 2 is negative 3/2. That can come in front of the integral sign. X divided by x cancels out. So we get negative 3 over 2. That comes out. The x's cancel out. The integral of e to the u du. Remember, the derivative of e to the x is e to the x. So the antiderivative of e to the x would be e to the x. The antiderivative of e to the u would be e to the u with respect to u. But again, notice all the x's disappeared. That's very important for us in the U-substitution strategy. So this is what we have. We know u is negative x squared. The integral of e to the u is just e to the u plus c. So we'll replace the u. We'll replace u with negative x squared. And this gives us y equals negative 3/2 e to the negative x squared plus c. But we're not quite finished here because we have this initial value. When x is 0, y is 2. So we're going to need to use that to solve for that constant. So we're going to plug the 0 in for x, the 2 in for y, and use that to solve for c. So y becomes 2. We see that. X becomes 0. So we get 2 equals negative 3/2 e to the negative 0 squared plus c. 0 squared is 0. Negative 0 is 0. So that's relatively easy for us to work with. E to the 0 is just 1. So we get 2 is negative 3/2 plus c. So 2 plus 3/2 is c. 4 plus 3, 7/2 is c. So to finish this differential equation, we're going to go ahead and replace this c with 7/2. So that our final answer will become y equals negative 3/2 e to the negative x squared plus c plus 7/2. You need to do that when you are given an initial value. Next problem is a little bit harder. We have dy dt equals 7y, and again, choosing to say y of 0 is 2. We need to separate the variables. I need all of the y's on one side, and I need all of the t's on the other. Now, how are we going to do that? Well, starting with the equation, dy dt equals 7y, I need this y on the left side, so I'll have to divide both sides by y. And I need the dt away from the y's, so I'll have to multiply both sides by dt. So first multiplying by dt, we get dy is 7y dt, not separated because I don't have all y's on one side and all t's on the other. But if I divide both sides by y, then I will have successfully separated the variables. At this point, I have to integrate both sides, the integral of 1 over y dy, the integral of 7 dt. Remember, the derivative of the natural log of x is 1 over x. So the derivative with respect to y of natural log of y is 1 over y. Do you see how this is really a 1 over y dy? So when we integrate that, the integral of 1 over y dy, integral of 1 over x dx, will have a natural log. So the integral of dy over y will be natural log absolute value of y. And we'll probably ignore the absolute values, mainly because in this course we deal with functions that are positive. Now the integral of 7, tell me a function whose derivative is 7 if t is your variable. Well, the derivative of 7t would be 7. So we get natural log of y on this side, we get 7t on the right side, but don't forget your plus c. So we'll say natural log of y is 7t plus c. In reality, it's absolute value, but again, we're going to choose to ignore that here. But what does the natural log of y mean? That is log base e of y is 7t plus c. So e to the 7t plus c equals y using our properties of the logarithm. Now, e to the 7t plus c, is there another way for us to think about that? Well, if you have the same base, you add the exponents. So e to the 7t plus c could be thought of as e to the 7t times e to the c. C is an arbitrary constant. E is about 2.718. So 2.718 to an arbitrary constant is still an arbitrary constant. So we're going to rethink of this as e to the 7t times some arbitrary constant. We're writing it this way first, e to the c times e to the 7t, and then e to the c is just an arbitrary constant c. So that's a little tricky for us to think about. But a constant to a constant is a constant. That's the key idea. Now we have this bit of information. Y of 0 is 2. So when t is 0, y is 2. So let's take a look at that. So let's plug that in. So y will be 2 equals c e to the 7 times 0. 7 times 0, of course, is 0. So we get 2 equals c times e to the 0. E to the 0 is 1. 2 equals c times 1. 2 is c. So the way we finish this differential equation is we substitute this 2 in for c, and we get y equals 2e to the 7t. Let's take a look at one more differential equation, and this will lead to a continuous compound interest model. The rate of change of the amount of money you have is 6% of the amount of money you have. This gives us a continuous compound interest model, and you're starting with $7,000. So let's go through the process. We need to isolate the variable, so first let's multiply both sides by dt. So we get dA is 0.06a dt. I need the a on the left side to isolate those, to separate the variables. So dA divided by a is 0.06 dt. Next, integrate both sides. Integrate the left side, integrate the right side. Now remember our previous example. This is the integral of 1 over a dA. Integral of 1 over x, natural log x, plus c. Integral of 1 over a, natural log a. We'll do the plus c on the right-hand side. Tell me a function whose derivative is 0.06 if your variable of interest is t. The integral of 0.06 will be 0.06t plus c. So left-hand side, natural log of a. Right-hand side, 0.06t plus c. Remember the natural log is log base e. So e to the 0.06t plus c equals a using our rules of logarithms. And same strategy as we did before, that'll be e to the 0.06t times e to the c equals a. But e to the c can be thought of as an arbitrary constant. E is 2.718 to an arbitrary constant is still an arbitrary constant. So we get e to the 0.06t times c equals a. I prefer to write it this way. So writing the c first, a is c times e to the 0.06t. Now what do we know? When t is 0, a is 7,000. That will enable us to solve for the arbitrary constant. Plugging in a 0 for t, 0.06 times 0 will certainly be nice, and a will be 7,000. So let's see how that behaves. Plugging in the a is 7,000 equals c times e to the 0.06 times 0. 0.06 times 0 is just 0. So I get 7,000 equals c times e to the 0. But e to the 0 is 1, so 7,000 equals c times 1. So 7,000 is c. So to finish this problem, all we've got to do is replace that c with 7,000. So we have a is c times e to the 0.06t. That will give me a is 7,000 e to the 0.06t. And you'll recognize that is a continuous compound interest sort of problem where your initial value is 7,000 and your rate is 6% per year. Kind of difficult to get that nowadays. So I'd like to just emphasize that fact by saying a is really a function of t. So the amount of money that you have on account, a function of t, is simply going to be 7,000 times e to the 0.06t. And that will conclude this lesson.